Okay, so now that we know how op amps work, we're going to start making some things with them. The first thing we're going to make is a comparator circuit. Now, we're going to take a break from negative feedback. Comparators do not use negative feedback. They actually use positive feedback, and we'll go into that in a moment. But it's a specialized nonlinear op amp circuit, nonlinear meaning that the output either goes high or low. It doesn't go anywhere in between. It's good. It's sort of a binary output, if you will. Matter of fact, they're used for analog to digital converters, as we'll also see. But it compares two input voltages and produces an output state that indicates which one is greater. They're always fast, very fast devices. They switch in nanoseconds, and they have other capabilities to optimize the comparison function. Let's see here if I can get my slideshow to work. Here's an example of a comparator circuit. Don't get too wrapped up around this differentiator or one shot. We'll actually do differentiators next week, and I'll explain what a one shot is. But I mean, you can obviously look ahead and see, but focus on this part, the left part of this little schematic here. This is actually a power failure circuit. This is a sine wave coming in that crosses 0 volts. So it goes above 0 volts and below 0 volts. All right. So it's an AC coupled sine wave, if you will. Now, this comparator is comparing this non-inverting input to the inverting input. And every time the non-inverting input is higher than the inverting input, the output is high, as shown here. Every time the non-inverting input is below the inverting input, the output goes low. So it turns a sine wave into a square wave, as shown here. And we'll not worry about the right side of this just yet. So whenever you're real close to 0, if I just go back right here, let's go back to the other, if you're real close to 0, okay, so this is 0 volts on the inverting input. If you're real close to 0 volts on this non-inverting input and you get some noise on it, what's going to happen? The output's going to chatter. You're going to see all that noise on the output. Basically, you're going to amplify that noise. So if you get a millivolt out of noise here and your comparator is operating at plus or minus 15 volts, then you're going to get almost 15 volts here on the positive side and minus 15 volts on the negative side. So comparators are real susceptible to noise unless you do something to them. We fix them with some positive feedback. So that's what this next slide is about. It basically amplifies the noise if you're not careful. So what we do is we add what's called hysteresis. And hysteresis, so here's a good diagram here. This is the noise on the sine wave, you see. And here we are, if we didn't have hysteresis, which we'll talk about in a minute, what would happen right here at this spot, at this 0 crossing here, is you might get a little chattering, okay? A little chattering right here on the output. In other words, it's going to switch high, low for a little bit while this wobbles back and forth. It doesn't show that it's going back and forth up and down across 0, but if this noise was a little higher, it would definitely do that. So hysteresis is incorporated by adding regenerative positive feedback, creates two switching points, the upper trip point, UTP, and the lower trip point. After one trigger point is crossed, it becomes inactive and the other one becomes active. So once you trip over the UTP, it's over with. Now you're going for the UTP. And we'll see, we do that with positive feedback. So here's the circuit. This is a Schmidt trigger, which is a comparator with hysteresis. And notice the positive feedback. Don't confuse this with the negative feedback that it looks a lot like what we did last week. But it isn't. This voltage divider is going to the non-inverting terminal. Remember before it went to the inverting terminal for feedback. This is a non-inverting terminal. And without doing any math yet, okay, think about how this circuit works. If this comparator is sitting at a high voltage, let's say it's top V out max, let's say 15 volts, okay? Well, we have 47K here and 10K here. If you do the voltage divider here, all right, you're going to get 10K divided by about 50 plus 10, right? So 1/6 of that voltage. So you take 1/6, if I've got my math right here, 1/6 of that 15 volts. That's the point at which this negative input or the inverting input has to get to in order for this switch to happen. Now, when the switch happens, okay, this goes in the opposite direction. This goes to minus 15 volts, let's say, which would be the minus V out max. And now you start all over. It actually reinforces the switch, pulls it away from where this was. And that's how the noise immunity happens, okay? So here's an example. And there you're going to use plus and minus 13 volts. So we have R2 divided by R1 plus R2. I guess this is 1/5, not 1/6. I was mistaken there. So 1/5 of 13 volts. Okay, so you get 2.28 volts. That's the switch point for the upper trip point. Now the lower trip point is going to be the same, except a negative voltage. Okay, so what that means is that when this input is high, all right, above 2.28 volts, and it's dropping down, okay, it drops down. It's going to, when it gets to 2.28 volts, all right, this output's going to switch, all right, and go to the other rail, okay, from 13 volts down to minus 13 volts. There's some homework examples on this and some examples in the text. You look at those very carefully. And if you have questions on this, certainly chime in on the discussion page. But the most important thing, I think, other than these equations are important. You put them on your equation sheet like I was saying last week. The important thing is notice the positive feedback here. That's important to remember. Now, if you need to limit the output, now we were going to plus 13 volts and minus 13 volts. If you want to limit it to a practical value, you can do output bounding, and that uses a Zener diode here. This doesn't have any Schmidt-Trigger hysteresis in it. This is just a bare bones comparator. But what it does do is it does limit the output to a positive Zener voltage. So if this Zener voltage is, for example, 5.1 volts, this is going to be 5.1 volts. It can't go, this output can't go any higher than that because the Zener's clamping it. Now the other direction, the Zener diode is forward biased. So there you get minus 0.7 volts. The Zener diode in forward direction is, of course, just a regular diode. And as an exercise here, what if you wanted to clamp it to two voltages, on a voltage on the positive side and another voltage on the negative side that wasn't 0.7 volts? How would you do that? Okay, well, there's an example in the textbook or homework where you have back-to-back Zener diodes here. So take a look at that example where you put back-to-back Zener diodes here, and what happens is you get a plus VZ plus 0.7 volts because the other diode is forward biased, the Zener diode's back biased, and when it switches the other direction, you get minus 0.7 volts minus VZ. So take a look at that example. But that's output bounding. Here's some applications. A lot of times comparators are designed to change a sine wave into a square wave. Okay, now this LM3111 is a special, not really special, but it's a very common comparator. It has an open collector output. Okay, so the comparator operates off of plus and minus 15 volts, but the output it's just an open collector. So you can pull it up to anything. So they're pulling it up to 5 volts with a 1K resistor. All right. They do have hysteresis. Notice it goes right here to the non-inverting input. All right. And it's variable. All right. It's variable. So the amount of hysteresis and the switch point will be variable here. Input is a red triangle wave here. This is a multi-sim example. 0 to 4 volts. Duty cycle is varied with R2. The duty cycle, the spot at which the switch happens, therefore it's going to cause the square wave to switch at different points, or to occur at different points along the triangle wave. All right. So I said sine wave. They're using a triangle wave. They both work the same way. Triangle wave is a little more linear, of course. So typically you'd use that for PWM, pulse width modulation. But either one, triangle wave or square wave, I'm sorry, triangle wave or sine wave will result in a square wave on the output. Just understand that. So with R2 set to 5%, a short pulse is a result. So this is a good example. It shows, and you could wire this up in multi-sim and see it for yourself on the scope on the output here. You just measure that output as they are here. This obviously isn't the display, but you would see that. You would see this display. Okay, now they're changing this up a little bit, putting ground reference to -5 volts on the LM111. All right, LM111 still has, and I think the other one was 111 too. 311 is a little higher performance than a 111. It's the same part, but 311 I think has a little higher performance. So we have a -5 volt reference. The ground reference is -5 volts, and that changes things up a little bit. It results in an offset of the triangle wave. So there's no hysteresis when R2 is set for 0%. The output is positive when the triangle is negative. So this is a symmetrical circuit. The triangle wave is going up and down past 0 volts. The square wave, because now we have a -5 volt reference here on the LM111 or LM311, it is now symmetrical across 0 volts too. Okay. Whereas before, we had a ground reference here on the LM311 or LM111. So this square wave, you see, was all above 0 volts. Take a look at the LM311 data sheet on digikey.com or anywhere you can find it. Have a look at it. You'll see there's some great good circuit examples probably from Texas Instruments there on the use of the LM311 comparator. There's also an LM339 comparator, very similar. I think it has a little higher output voltage capability, but it is also open collector. Open collector, let me go over that a little bit more. Open collector on this output, this is pin 12 here, I guess, or I don't know what that is. It's hard to see, 17 maybe. What that means is it's not a push-pull totem pole output. In other words, it's not driving high or driving low. It's only pulled low by the transistor. Okay, the collector is pulled low when the transistor saturates. But when the transistor is not in saturation, when it's in cutoff here, this is a floating output. It's just a collector that's floating. So that's why it needs to be pulled up. And in this case, it's pulled up with a 1K resistor. Okay, and R2 is set at 100%. The rising edge of the output appears near the negative peak. Upper and lower trigger points when R2 is set to maximum. Well, 100K is R2 maximum. So 100K divided by 127. 127 is 27K plus 100 times the upper trip point. No, I'm sorry, not upper trip point, the output maximum, which is 5 volts, So the VUTP ends up being 3.94 volts. So that's where it's going to switch. Okay? And it's going to switch at minus 3.94 volts too, because it's symmetrical. A couple of more comparator applications. Doing some analog to digital conversion. You can create this resistor ladder and hook up a bunch of comparators to it. Each one of these comparators reference points, which is fed into the inverting input, is sitting at a different voltage. Okay, so here's the reference voltage here, but each one of these points, since it's a big long voltage divider, is a different voltage, right? Because it's a big voltage divider. So as your input goes up and down in voltage, it'll climb up and down this resistor ladder in voltage, and each one of these comparators will fire at different points along that analog voltage, creating different bits. In this case, there's 8 bits. And we have a priority encoder here, which turns these 8 bits into 3 bits as a binary output. Right? So it's called a flash ADC, flash analog to digital converter. They're very fast. They are used, but they're not very high resolution. There's a lot of parts you need in them in order to create a high resolution output. This one only has 8 levels. Okay, that's it for comparators. I'm going to switch hats now. We're going to go back to our negative feedback. Okay, we have a feedback resistor going to the negative feedback, going to the inverting terminal. And these are regular OpAmp circuits. They're inverting OpAmp circuits, but they have more resistors on the front. Okay? And these are summing amplifiers. And as the name implies, it sums these voltages. This is going to be Vn1 plus Vn2 plus Vn3 equals V out, if all these resistors are the same value. In other words, R1, R2, R3 all equal RF, which is 10K. There's some examples here. So if all the resistors are 10K, if the Vout, the input voltages are 5 volts minus 3.5 volts and plus 4.2, what do you get? Just add them up, you get minus 5.7 volts. Now, something you have to be careful of here is, you know, that this OpAmp, it's not a comparator anymore. Well, it still could be if you used it that way, but it's not being used that way now, right? Because we have the negative feedback. You have to be careful because these OpAmps only have a limited supply of voltage on their power supply. So I'm running this at plus and minus 15 volts. The sum of all the voltages on the input have to be below the absolute value of 15. So it has to be, you have to add them all, together. It can't be greater than 15 volts or less than minus 15 volts. It has to stay within that. Otherwise, the OpAmp runs out of headroom. Okay. So there's other types of these. There's an averaging amplifier. You can take your feedback resistor and make it 1/3, in this case for 3 inputs, 1/3 of the input resistors. So in this case, 3.3K, R1, R2, and R3 are each equal 10K. And so we do a little example here. 1/3 of the 3 voltages, you end up with minus 1.9 volts, which is the average of all those. Now, of course, it does invert it. You get the minus version of it, but you can flip that back around by using a unity gain inverting amplifier, which you all know how to do from last week, right? Look that up. So V out is going to be the average of all of those. Now, what if you have 4 resistors? In other words, 4 input voltages, all 10K. How do you do it? Oh, you have to change this RF from 3.3K to 10 divided by 4, which is going to be 2.5K, if my math is working. So that resistor would change to 2.5K. And you'd get the average of all 4, and so on. Okay? So that's an averaging amplifier. There's also a scaling adder. Now, scaling adders is where you have one feedback resistor, in this case 10K, and each one of these input resistors is different. It's going to give a different weight to these inputs. And so here's an example. This is a good example. We have 3 microphones. The first 2 microphones, require a gain of -2. And the third one requires a gain of -3. So the values, if RF is 10K, so for R1 and R2, you have 10K divided by -2, which is that gain, and you're going to get a resistor of 5K. For the third one, it's divided by -3, so you're going to get a 3.3K. Now this is an interesting example because I'm sure some of you are familiar with mixing consoles, audio recording mixing consoles and things like that, where you mix different audio sources. Well, the pan pots on those things, right, are these resistors, R1, R2, and R3. And certainly there's mixing consoles with hundreds of channels, so you could have hundreds of these resistors. The pan pots are variable resistors. They're potentiometers. So these resistors are each potentiometers. And what that does is it gives your microphone for the lead singer here, the microphone for the backup singer here, the guitar amp here, and keep going with resistors. The bass amp, the drum, kick drum, the bass drum, the organ, the trumpet, you name it. You have all the different channels of audio here, and the audio mixer is changing these resistors with their potentiometers, or sliding them up and down to give these different relationships for different scaling or different weighting for each one of these inputs, so that they're either louder or not as loud depending on how the mixing engineer is setting up the track. Okay. Another application of a scaling adder is putting these fixed resistors in here, and you can do a D to A converter. Okay, so each time you flip on one of these switches, you're turning on an input and summing these values into the summer or to the adder. Now notice that these are different weights. This is whatever R is, RF. This is 8 times that R, this 4 times that R, 2 times that R, and then just R. And that results in these binary weights, 2 to the third, 2 to the second, 2 to the 1. Okay? It's a digital to analog converter. And then R2R ladder DAC is another example of using a scaling adder. We have these resistors, which are all the same resistor, and this is really can be done very accurately on a single substrate. These resistors are not necessarily discrete resistors. They're on a silicon substrate, and they may be 10K, 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 10K. These 2R is 20K, 2R is 20K, and so on. RF equals 2R, 20K. But the good thing about putting them all on the same substrate is that it can be done very accurately. They may be not all equal to 10K, 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 and 20K, 20. They may be 10.1, all right, down here. But the good thing about the 2R, what happens is they become 20.2. So they're all off by the same amount, and so it still works. So that's how these are made. They're made on a common piece of silicon. Even the OpAmp is in there. All right, so these R2R ladders and DACs are very accurate. There's some math you can do on this too. We don't, usually in my regular face-to-face class, I don't do the math too much because it's a little, and it's really not necessary, but just understand that an R2R DAC, it does have a high accuracy and uses all the same resistor value, which makes it very practical. And I think we're done. Now we're going to do the integrator next week, integrator and differentiator. So we have that to look forward to. And then the following week, we have our first midterm. So Everybody be safe, and we'll see you next week. If you have any questions, please post them in the discussion section. Okay? Take care. Bye-bye.